Hello. Mm, Today we will discuss about the multi-channel analysis of surface wave. So at first we have to know the seismic waves. Their seismic waves come from any source where impact through energy, and it come from any parts of ground to another parts, so and then create wave, uh, and it will disturb the ground. So this wave, like one first body wave, it is travel through, here you can see the figure, travel through the earthwork, earth. This is body wave. They are divided into two parts: PE wave, primary wave, and secondary wave. Primary wave, it's a motion, and here primary wave, you have motion and of the and direction, motion of the particle and direction of the waves is, wave propagation are the same. Here particle motion and wave also, wave propagation direction is the same. And then secondary wave, S wave, this motion of the particle and motion of the particle up and down. Okay, up and down. uh, and but the wave propagation, the direction is the perpendicular. So here this is the shear wave, I can say, or transverse wave. And there another wave, surface wave. This, you can see first figure here, surface wave. At the at the surface, the wave is propagation and sewing. So here, there the waves are traveling through along the surface or along the earth. Here two types of surface wave: lava waves, which the particle motion and vibration perpendicular to the direction, like shear. This is lava wave. This the particle motions here and here, you can see the direction. Okay, but wave of the propagation, is direction is the perpendicular. So it's like same of the shear wave, but is secondary wave, but different direction. So this is the lava wave and relic wave. From the relic is a researcher. So this wave, elliptical motion of the particle is perpendicular to the surface. Here the this particle motion is like that, particle motion like that. So this is the motion of the particle. So and wave also, wave direction is the also perpendicular to the surface. So like that. So this depth motion can reverse to retrograde. Elliptical motion, the retrograde to prograde. So you can see the relic wave. So we will discuss about the relic wave through the this test, multi-channel analysis of surface wave. And next you can see the direct wave. Here, direct wave symbol. This is the direct wave symbol. And this wave indicating, if this is the is a image through the software, and detect which is the is this a distance, or if it is the time, so this image scanner will be see like that. This wave is the direct P wave and reflective wave. So if the there is two layer, if reflection diffracted it, so here, and then here something refraction. So the and this type of wave indicating the diffractive wave. If the air sound wave, any noise or air wave from any machine or any high voltage electric wire or any air, so this is this type inclination wave is so indicating the this type of wave, surface wave. And if ref, reflected wave, if directly reflect from one layer, so it is horizontal wave. And some effort for next the sinusoidal wave is indicating this the reflective wave. And surface wave, here we can see the surface wave. So I have to today we will discuss about surface wave, how to measure it. So is velocity. So here this surface wave, sinusoidal wave is increasing with the time and increasing with the uh, distance. This is increasing with the distance and increasing with the time. So it is indicating the surface of this image. So this is a black and white scanning image. So, and then today we will discuss the multi-channel analysis surface wave. So this is a non-destructive surface wave velocity measurement test. So to determine the soil property require physical forward solver and back calculation algorithm to fit the field measurement. And this follow the ISTM D5777, and also can follow IS code 15681. And what the role of the this test? So we can use this test to measure to evaluate the ground stiffness by measuring shear velocity of the surface. So we can measure up to 0 to 30 meters of the surface of the or of the earth. And uh, with the frequency between we can the source energy source, you can produce frequency and measure up to 4 hertz to 80 hertz. And then we can determine it if we can use for the geotechnical engineering property of this earth or my earth material. And also we can determine the density of the some earth material, Poisson ratio of the earth material, and shear velocity of the shear velocity of the uh, is close to related to also young modulus, hair modulus. So which will be used for geotechnical designing or geotechnical analysis. So here in this figure, one recording van is there or any machinery van. Though here geofan is laying his hair, and another the source seismic source here. So this seismic source produce the wave, okay, energy wave. And this wave is reflecting from the different layer, okay, different layer. So and it is receiving that at first it is receiving the first geophone, then receiving the second, the so many yeah, up to oh, 24 or 46 geophone can receive it. It depend on the how many depth required for analysis. Yes, so geophone will increase if want to do want to do increase them our depth have to measurement. So here if we increase the frequency, so it will increase the depth to measure. So here you can see, so here different third layer, it's reflected the wave and collecting from the receiver, receiving through the geophone. So this type of testing will follow through the test. So we can measure the different layer thickness, okay, through this test. Next, so what is the use of the why you will use the MSW test? So if one where one thinks And so if we can measure the through borehole, okay, here one borehole have done, but this borehole result will not same uh, at the position of here. So here we can see that this is low density of the material, but here this is ending, but here is different. So borehole test will be done up to apart 15 or 50 or 100 meters, but in 100 meters or 50 meters the layer can be changed. So that's why we have to measurement or have to analyze the layer of the if ground onto through MASW test, and if is a very high superstructure or very sensitive construction will go on, or any other activity will go on this ground or earth. So is required. So we can see there one borehole cannot measure the whole area material properties. And then next, if you done and the CPD test also, where one CPD test here in done like in the through the along this line, but here this low compressive low strength material or loose material is here, and but at this position this is the different material starting from here. So uh, within 10 meters the layer material are changing. So it is very challengeable, or it is very unsafe for any structure or any ground stability. So here we can also see, we can also determine after any construction and or any slope of, through the geophone on or MASW test, we can determine the compaction and layer thickness. Here we can see that the layer, different layer and different shear velocity in giving. Okay, increasing the shear velocity, increasing the depth. Okay, and the shear velocity also giving the this density and compaction. So we can check the slope stability, we can check the ground compaction, and okay, and for any pavement or any railway or highway pavement earthwork. And also we can see for the any offshore construction, and due to water, or the borehole test or CPT test is not accurately. So in MSW test we can cross check through MSW test. So here you can see one and wind turbine is here, but they are at this time there are some low strength material, earth material is there. So here you can see. So as per analysis, this are the ground material. So design will be the wind turbine design. Other any structure can design or ground improvement require government will be changed. Okay, so this result we can found the through MASW test. And also if you want to determine the liquefaction area, here one line is here, one line is indicating here, represent here that the different layer is starting from this position. So here loose material or liquefied material layer upper side, and also here this rock type or some stiffness, high stiffness material is upper side of the lower stiffness material. So this line is representing that the liquefaction can occur or slipping can occur from this stiffness material uh, from this stiffness material. So so we can determine it. It's maybe happened. So as per this situation, we can and take precaution. And next time, we'll see. Yeah. Mm, if want to do stabilize the any soil or ground or improvement there have no for economically or sustainably, so we can mix any chemical composition with soil, just like grouting or any other chemical material, or improve with through geosynthetic or any dynamic compaction. And so we can see here their image, if improving in increase, stabilizing increase. So this MSW test will be MSW this image will be from low stiffness to higher stiffness. So it will increase mean improvement is compressibility increase, com, com, compression increase. So compression increase, also stiffness increasing. So here stiffness increasing. So, so we how we measure at this. So it is the easy process and economical process as the MASW test is to determine the soil stabilization process. So here the is getting in lower stiffness to higher stiffness. So okay. And then how the test will be conduct the multi-channel analysis of surface wave. Surface wave, uh, at first, surface wave how will conduct. So we have to produce one or waves. So how waves will be produced? So here some one plate, it here steel plate here, and one hammer, sledgehammer is here. Just 6 kilo to 10 kilo you can use. It is hammering on this plate. So this plate energy, it will be created one waves. Then waves going frequency, like waves, the frequency will be receiver, the waves will be receiver through this geophone are in a line. Geophone are placed in a line, and you can see there are same after same difference distance, and like 1 meter, 2 meter, if you want to increase, so you can increase as per the depth of the ground, required depth of the ground. Here one seismograph machine which will be collect the data through geophone on here, and also there one seismic recorder are recording the data or operating from this is control unit. So left in the this the one software will be control the this test, and which option will be required. So these all connected through the cable. There are connecting cable, and there are Ethernet cable with the seismograph, and all this seismograph power supply through the battery. So here the person will is hammer here, and wave will receive from through the geophone, and geophone from geophone the seismograph will collect the data as time and velocity, and it will and frequency, and the control unit will record it. So next, after after that, and the and during the MASW in test, this collecting the data as a like a time And offset the multi-channel recording the time and offset the offset one this if multi-channel up to 1 meter, so here indicating one line is one geophone. So one geophone. So here one source or from starting from here and starting from here and collecting the data starting from here, and after 15 in meter distance one geophone is has placed. So so it will when the geophone will collect the receive will receive the wave, so it will show at the display of the control unit and the time versus offset. So when increase the length of the geophones and it will be in increase with time. So it will take time if the wave receive to long distance through geophone. And then after receiving the data through software, we can determine the phase velocity, also and with the frequency. Phase velocity from time and distance, this software will get the phase velocity here also with amplitude. uh, and here this and then it will create the dispersion curve here, dispersion curve. Okay, this is the dispersion curve, we can see here. This is the dispersion curve here. This portion is this portion. So I have to select the top peak point and for dispersion curve, and then it will normalize the amplitude and with frequency and also phase velocity. Okay, then it will produce it will calculate the wavelength versus phase velocity. Okay, so after wavelength versus phase velocity, it will measure the depth versus shear velocity. So uh, first phase velocity versus frequency, then it will calculate the the dispersion curve, and from this dispersion curve will be calculate the wavelength versus phase velocity, and then phase velocity and to wavelength form to it will calculate the depth versus shear velocity. Shear velocity will which service is representing that depth of the layer and depth of the different character is layer. Okay, so we can see through the this MSW test. Also same things here. mm, this the control unit display, we can see here this different geophone will receive this data, and then it will convert into phase velocity to frequency inversion and process as, and then it can determine the depth versus as phase velocity, a shear velocity, sorry, shear wave velocity, and shear wave velocity will make this image of the ground layer. So here this low shear wave velocity here representing the blue, and high shear wave velocity representing the with the red and black. So it is indicating that they are low thickness soil uh, mm, at the upper side of the ground, and then increasing it and stiffness increasing, here the maybe rock or maybe higher stiffness material is there. And then if it here there is some difference will create, and some if it increasing the source of the seismic or source of the wave, source of the energy. So if it 10 meter, okay, 10 meter, it will we can measure the if at a respect of 30 hertz frequency. So if it increase the source, so the peak point will be peak point. It is sharp. If in peak point is disturbed, if it, so close source was giving the sharp of peak point of amplitude. So it is better the source is within the 30 meters, okay, uh, closely. And if there are another things, if we can say there the length of the 46 24 3 geophone, if length of the 23 geophone is the apart or difference distance is 0.5 meter, here total length is is 11.5. So here peak point is peak point is sharp, okay, uh, peak point is sharp amplitude, amplitude peak point is sharp. And it is increase it. So there are so peak point or difference peak point with different amplitude, okay. So a peak point is disturbing. And if it is increase the frequency, if you increase the 20 hertz to 40 hertz, so also we can see if you the increase the frequency, the peak point is also sharp. Peak point is also sharp. There are some elliptical type. There are some peak edge, sharp edge type. So this is a better if the peak point is sharp. So we have to increase the frequency and also increase also we reduce the geophone, the like 1 meter apart distance. It is better. So then we also see here some challenges here there. If it's a multi-layer, there are the higher stiffness between two lower stiffness. Here, case one, where the stiffness is increasing. Stiffness is increasing, but so we can see the phase velocity dispersion curve, velocity dispersion curve reduce with the frequency. But when it is one higher stiffness layer, it is between the lower stiffness two lower stiffness layer, or somewhere one lower stiffness layer between the higher stiffness layer, and so it will indicate the discontinuity, like that. It is a continuity dispersion curve, but this curve is discontinued and not continuous. So it can indicating or representing that there are something different layer. So here you can also say some higher stiffness layer is between two lower stiffness layer. Here some higher, lower stiffness layer between two higher stiffness layer. Also we can see the result of the this and inversion process. After inversion process, there's here uh, we can see there one here. There S velocity and P velocity increases, okay, and also increases as the density, and also you can see the thickness not increased, but one for increases the 1780, फिर 12180, and then again 1780. So one different layer between there. So that's why this dispersion curve is discontinuous. So this result we can see also compare with this graph. Okay. Here are some result from researcher, that the mm, uh, we can see here. If it's the sand is lower wave velocity, and also it is a much greater shear wave velocity. The basalt also get a shear wave velocity, and also as per geotechnical step, and the hard rock is is greater or much shear wave velocity. Okay, uh, but here you see the steep soil. There we can see the range 180 to 360. Very dense soil 360 to 780 meter per second. A rock 760 to 1500 meter per second. If this is the some clay soil or low deepness soil, this is we can see the less than 180 meter per second. So from this velocity we can indicate the layer of the ground. Here one some uh, normalization formula from Fourier transformation. Um, we will to convert from the velocity to amplitude, and then convert into shear wave velocity. So here we can see this the first velocity wave velocity determined, this normalize it, and then phase velocity, and also calculated the amplitude. After phase velocity is calculate the amplitude through this equation, and then it calculated it showing the dispersion curve. So after collecting the data, this chart formula or can use for or making the dispersion curve. So it is like a coding type software, coding type. So yeah, we can measure also through theoretically through this is Fourier transform formula. So it is using in this test, using many researchers using the Rayleigh wave velocity test. So Rayleigh wave phase velocity test was following. So elastic theory is used to convert Rayleigh wave velocity, and then to shear wave velocity, and to then it is converted into stiffness. Here phase velocity, it is distance between the two geophone, and also taking different time of the two geophone. Here the Rayleigh wave velocity into frequency into the wavelength. This formula we can use, and Poisson ratio if this measuring this formula with the p velocity of the primary velocity and secondary velocity, measuring this the Poisson ratio. We can use this correlated Young modulus with the shear velocity and also density, and also the with the Poisson ratio, and shear velocity also with the Poisson ratio into multiplication with the Rayleigh wave velocity, and also shear modulus also correlated with density of the soil and shear wave velocity. So here velocity, we can measure frequency by the wave number, uh, wave number. So and then wavelength is 2 pi by wave number, and wavelength, and then we can use the velocity of the wave with amplitude and phase velocity. So here this geophone.
Hello everyone, guys.
This is connected cable with the system. Here this is connected with geophone. Geophone was penetrated in ground. And here the gap between the geophone is 1 meter and first one 2 meter, and here the plate hammering here to get the wave, and then so both side geophones cable connected with this seismograph unit, and also laptop also connected, and battery also connected with this seismograph unit. This is approximate 15 lakhs value of this machine process, and we will control from here. During control unit, first the acquisition configuration at here the mold check the mold for sensitivity, and then sample here periods. We can take the 500 millisecond and their frequency 20 hertz to 2000 hertz. Then there will be in the pre-trigger time how much will time taken required before the hammer, and so it is 10 millisecond very negligible, and their acquisition time how much time want to take you take your data after hammering. So it will take the 1 second, and if we increase it will increase the time taking time data recording. So then high pass filter will be conduct it will be recorded at above the frequency, and the low pass filter below the thin frequency, and then it is NAND, and then notch filter. It is a high voltage electricity wire here. So for India is 50 hertz, and in Italy for 60 hertz. Here in now here is none. Then striking in here the nong of hammer for required for the striking, and then the geophone configuration. Geophone configuration is in the first geophone is 0, and after increment it will increase 1 meter, or we can see here the then the trigger source it is minus 2 meter here, or from first geophone is 0, and then the source is minus 2 meter, and we can increase the x value from here 1 meter or 1.5 meter or 2 meter, increasing is the part of that geophone between two geophone distance. And then save the configuration. Here we have to give the name as per name and new name here. Then we can save here every test data through the name, and after saving this here the geophone noise monitoring, we can see here display the here the receiving the frequency through the geophone as per respect to the distance and with the time in the sinusoidal wave, and here the gain test is for the take one shot and adjusting the data according to the test, and tier to 0, and again it will take the data and tier to the 0. So I can we can see that here the one geophone disturbing by through the 1%. So here you can see the how the wave the frequency is collecting in through that here. So starting the hammering, it will take saving, and then second hammering, and we here will take the 6 hammering for acquisition and view the result after that. First one person hammering on the plate, and then it will take it will receiving the frequency through the geophone. So here which is wave traveling through the ground on up to geophone. After receiving the after acquisition and the data through this seismograph unit, it
it collecting it is will showing the result. Here we can see the time, and as per respect with the geophone number or distance of the offset. It's here after saving the name of the file, we can see the display, or after that this result will send to software for our dispersing curve, and will creating the info file of the image. This software we in this test we can easily and very will take less time and economically we can determine the soil layer profile. Here the we can see display there the our testing result and the file opening, and then we'll see the result of the time velocity. It can determine the velocity distance versus time, no, the wave velocity. Here Gigaseismic Pro 7.1 software is using, and so we'll find the left side box, we'll find the our file, and so we can search the file through the memories. And here after selecting in the our saving files is of the test, and it will open, and so oh, we can see our test result. This is different geophone, and so very less difference or very less sharp, as we cannot see open eye of the frequency receiving gap difference. And so after that it is amplification and multiplication, we can clearly filter it the proper the graph. So